Hey, this is Mr. C, and this is Unit 1, Lesson 1, Ready, Set, Go. Okay, for each of these triangles, these right triangles, we're going to find the missing side, and one thing here to note is that we are going to leave our measures in exact form, so we're not going to be using our calculator to find square root. So each of these right triangles means that we're going to be using Pythagorean theorem to solve for our missing sides. Remember that C is the hypotenuse, so the longest side. So for example, in number 1, that is C. So the side that we're looking for, that X, that is our hypotenuse. So setting up Pythagorean theorem, we'll set up 3 squared plus 4 squared equals x squared. 3 squared is 9. 4 squared is 16 equals x squared. 9 plus 16 is 25 equals x squared. Then we're going to take the square root of both sides. And the square root of 25, actually that comes out to exactly 5, so that one has an exact answer. Moving on to number 2, we'll put an X there where the question mark is. And again, that is the hypotenuse. So, setting that one up. 5 squared plus 12 squared equals x squared. 5 squared is 25. 12 squared is 144 equals x squared. Adding those together, we get 169 equals x squared. Take the square root. 169 is a perfect square. It's 13 times 13, so x is equal to exactly 13. Okay, for this one, this time the hypotenuse is 4, so that is going to be C. And 1 and x are going to be our legs. Oops. 1 and x are going to be our legs, and 4 is going to be our hypotenuse. So 1 squared is 1, plus x squared equals 16. So from here we're going to subtract 1 from both sides, and then we get x squared equals 15. Take the square root of both sides. Square roots and squares cancel out, and we get x is exactly the square root of 15, and we're not going to plug that into a calculator. We're just going to leave it in its exact form. Number 4. So let's find our hypotenuse. That's this side with the root 10. Put an x for our missing side. So our equation becomes 3 squared plus x squared equals square root of 10 squared. And this looks a little confusing, but actually this makes things a lot easier for us because squares and square roots cancel it out. So what we're left with is 9 plus x squared equals 10. So from here we're going to subtract 9, minus 9, minus 9. And we get x squared equals 1. Take the square root. And the square root of 1 is 1. Number 5. There's our hypotenuse. X is one of our missing legs, so we'll set this one up. 2 squared plus x squared equals square root of 13 squared. 2 squared is 4 plus x squared. Squares and square roots cancel out, So we're left with just 13. Subtract 4 minus 4. We get x is equal to 9. Oops, sorry, not x, x squared. We're going to take the square root. Squares and square roots cancel out, so we get x is equal to 3. And for our last one, there's our hypotenuse. Put x for our missing side, so x squared plus 4 squared equals root 17 squared. X squared just says x squared. 4 squared is 16. And squares, square roots cancel out. Oops, no, that's 16, 17. We'll subtract 16 from both sides. And x squared is going to equal 1. Take the square root. Square root of 1 is 1. Okay. Onto the set. Name the single transformation that can be used to carry the pre-image to the image for each pair of insects. So for A, this is clearly a rotation. The head of the ant is facing up and then it's facing to the left. So this is a 90-degree counterclockwise rotation. For our little grasshoppers here, that is a mirror image of them. They are being reflected over that line, which is the y-axis. So we are reflecting over the y-axis. And for our next shape, due to symmetry, it almost looks like it could be another reflection. But I'm going to say that this actually looks more like a translation based on where the spots are on the ladybug here. I would say that this guy is moving. If we can find a point here. It's going about 4 down. And roughly 5 to the right. That's a translation. About 4 down and 5 to the right. Okay, number 8, we're going to be flipping back to our previous lesson, lesson 1, and in order to visualize some of these things. So we're determining whether these statements are true or false. So in a reflection, pairs of corresponding points lie on parallel lines. Well, if we go to our lesson 1, we look at our reflection. There's our reflection. Yes, those are parallel lines, okay, to our corresponding points. So that is true. Okay. So true. Okay. If we have some line of reflection, each of our points can be some distance away like that, and they will be parallel to each other. Okay. In translation, pairs of corresponding points are on parallel lines. Again, we can check that in our lesson if we go to our first translation. So yes, those are parallel lines. Okay. So true. Okay. In a translation, each of our points moves same. Let's do this. Same distance and same direction. Okay. So there's a picture of our reflection. There's our translation. In a rotation, pairs of corresponding points are on parallel lines. Got our rotation. These, our image will load here. There we go. These are not parallel lines. They are what we call concentric circles. Okay, so not true. Okay, that is false. Okay. So all of our points are going to be moving in these concentric circles. A little better. Okay. So there's our rotating points. So they'll move along these curved paths here at the same angle. All right. In a reflection, pairs of corresponding points lie on segments perpendicular to the line of reflection. That is true. Okay, so each of these segments is perpendicular to our line of reflection. Okay, so that is a true statement. In rotation, pairs of corresponding points lie on concentric circles. We just drew that, we just saw that. That is exactly what happens. In a translation, pairs of corresponding points lie on concentric circles. That is false. That's only for a rotation. Okay, again, translation, we have these parallel congruent line segments. Okay, they're all the same length, same distance, but they're definitely not circles. Okay. Form the transformations as described. Focus on the anchor points. Okay, so which is exactly what I'm going to do. I'm not going to bother trying to be super accurate with my sketches here. So on this grasshopper, let's focus on first this first point right here, and then draw the rest. So this one is going right 4. 1, 2, 3, 4, and up 3. 1, 2, 3. So that's where that leg is going. So dot there, and then just relative to that, there's another little dot there, and then 2 more there and there. This dot goes right here, and I'm just kind of figuring out where the rest of my anchor points go relative to that first one. Point there. Roughly a point here. Okay, so there's all my anchor points. And I can try and sketch this. This is not going to come out very well because I'm not a very good artist. But there's the one leg, little, I don't know, other leg-like thing coming here. Head, 2 antennas, body. There's the body, got one leg coming here, another leg coming here. This body, and then a leg coming here. That's my rough sketch of Mr. Grasshopper here. Reflected ant over the line, y equals negative x plus 2. Create anchor points as needed. So let's put some anchor points on each of the legs. And right at the front of his head and at the back of the thorax. Okay, I'm going to use a ruler here. And just sketch perpendicular lines at the same distance away. Okay, and we'll just put points at the end of those lines. Too far. Let's try that again. That's 1, 2, 3. 3 little ones. 1, 2, 3. There we go. Okay, so now I have a lot of where those anchor points are going to go. There. Okay, I think I have enough. Something like that. So, here's where this is the head right here, so mandibles coming out. section like that. And the bigger thorax, something like that. And then figure out where these arms and legs go. So these middle ones seem to go straight out like that. These ones seem to go like this. These ones tend to go back like that. That's my rough drawing of my ant reflected. Okay, not bad for somebody who's a terrible drawer. Okay. And then our go. Graph each function. So remember our y equals mx plus b. M is the slope. B is the y-intercept. So there's our y-intercept. We'll start there. So down 1, 2, 3. There's our y-intercept. Our slope is 2, so we're going to go up 2 over 1, up 2 over 1. Okay. Could even backtrack that 1 point. And go ahead and connect that with the ruler. There we go. All right. This one, y-intercept -3 again, but this time our slope is down 2 over 1. So I'm going to backtrack that. So constantly going down 2 over 1. Graph that. Okay. All right, what is the one similar and one difference between these two functions? Well, they both have the same y-intercept. So same y-intercept, that's something that's the same. But they have, the first one, 11, has a positive slope. While 12 has negative slope. Okay. 14. Again, start with our y-intercept at 1. And then take our slope. 2 over 3. So up 2 over 3. Up 2 over 3. So I can backtrack that. Okay. Good enough to get aligned. Okay, and then for 15, there's our y-intercept again at +1. And then a negative slope of down 3 over 2. So down 3 over 2, down 3 over 2. Backtrack that, okay. There's our line. So something that's similar and different. So again, we have the same y-intercept. And this time, not only is our slopes, one's positive, one's negative, but the slope fractions have been flipped. Okay, so the slope are opposite, meaning different signs, reciprocals, meaning fraction has been flipped. All right, and then our last two. Y-intercept is 1 for the first function, and then our slope. Well, we can't see here, but there's really a 1 in front of that, so it means their slope is positive up 1 over 1. 1 over 1, up 1 over 1, up 1 over 1. Okay. There we go. Okay. And then for this one, our y-intercept is -3. And again, we have that slope of 1, so up 1 over 1. We'll line that up. There we go. So, something that is the same. Well, these have the same slopes. And you might notice that they are parallel because of that. What is different is that they have different y-intercepts. And that is the end of this Ready, Set, Go.